Cool. Hello, hello. Hey, how's it going? I'm Bashar. I'm a PhD student at NYU. And it's truly a pleasure of mine to be here to present our work on user-centric gender rewriting. This is joint work with my PhD advisor, Nizar Habash and Houda Bouamor. So starting off with a motivating example, say you have an MT system that is trained to translate from English to a morphologically rich gender marking language like Arabic. And for instance, let's say we have a sentence like, I'm a wonderful doctor, where the user gender is underspecified. We notice that the MT system will pick a user gender at random when it generates the Arabic translation. And in this case, the MT system generated the masculine Arabic translation of the input sentence. Now, for some users, this is the correct answer, but obviously not for others. Now, this is a common experience the speakers of morphologically rich gender marking languages face when they use user-unaware NLP systems. So how can we fix this? In this work, we define the task of gender rewriting as generating alternatives of a given sentence that match different target user gender contexts. And we focus on Arabic, a gender marking morphologically rich language. We develop a user-centric gender rewriting system that takes as an input an Arabic sentence, which could be the output of any black box NLP system, and a target user gender. And the goal of the system is to rewrite the input sentence to match the given target user gender. So for instance, if the input sentence that we are dealing with is the masculine Arabic translation of I am a wonderful doctor, and our target user is a female doctor, the MT system would basically rewrite that input sentence to its feminine form. However, if the end user was a male doctor, the input sentence will be passed to the output as it is, since it was already in its masculine form. Now, before we go into the data and the model we built, we would give an overview of Arabic linguistic facts, given that not many of you speak Arabic. So Arabic is a morphologically rich gender marking language that inflects for many things, such as gender, number, person, case, and so on. There are around 22,400 par speech tags in Arabic compared to the 48 par speech tags in English. In terms of its orthographical ambiguity, there are 3 different core meanings and around 7 different diacritizations per word in Arabic. Now, when it comes to grammatical gender has a binary value. So it's either masculine or feminine, and it applies to verbs, nouns, and adjectives. At the word level, grammatical gender could be expressed either through the base form of the word or through pronominal enclitics. Now, changing the base form gender of the word requires us to do either a lexical change or a pattern change or a suffix change, as you can see in these 3 examples. When it comes to pronominal enclitics are basically suffixes that attach to words, but they refer to pronouns and they do mark gender. So in order for us to change the gender of the words, we will basically need to change those pronominal enclitics. In more complex cases, we need to do a combination of all of the above. So as you can see, this is not an easy problem, and it requires a lot of changes to the word, basically. Now, as a disclaimer, we acknowledge that by limiting the user gender choices to the grammatical gender choices in Arabic, we are excluding non-binary gender and no gender expressions. We are aware that there are some grassroots efforts in communities of speakers in Arabic who are trying to basically use no gender expressions, but this is not the mainstream currently in the language usage. Now, in terms of the data that we used to train and test our systems, we used the Arabic parallel gender corpus, which is a parallel data set that we developed last year. We selected sentences from the Open Subtitles 2018 data set. And the sentences basically have word level gender annotations to indicate the gender of either the speaker and the listener of every word in the sentence as either masculine, feminine, or ambiguous. The number part of the label basically indicates the first person or the second person for the listener or the speaker. In this work, we extend the word level gender annotations to mark both the base form of the word and the pronominal enclitics. So every word will basically get a label one label from 25 labels, such as 1m plus b, 2m plus b, and so on. Every sentence in the Arabic parallel gender corpus has a parallel version to indicate its rewritten gender alternatives if that sentence has a gendered reference. If not, its parallel form will be basically a trivial copy. Moreover, the Arabic parallel gender corpus has 5 different balanced corpora plus English. So the input corpus, where you can think of it as the source, and 4 different target corpora to basically model different target user gender contexts. In terms of the statistics, there are around 80,000 sentences in the corpus, and 54% of them contain gender references. Whereas in terms of the word level statistics, only 10% of the words are gender specific. In terms of the splits, we use 7-1-2 for training, development, and testing. And now I'll describe our multi-step gender rewriting approach. So to do this, we developed a multi-step system that has 3 main components. A gender identification component that basically identifies the gender of every word in the input sentence. The second component is out of context word gender rewriting. And the third component is in context ranking and selection. The first component is basically a word level classifier that was trained by fine-tuning a model called CamelBERT, which is a BERT model that was pre-trained on the largest modern standard Arabic corpus to date. For the out-of-context word gender rewriting step, we developed 3 different rewriting systems. The first one we call corpus-based rewriter, or corpus R. This is basically a simple lookup model that is trained in a maximum likelihood estimation. So given a bigram context and a word level gender, we would like to basically find the target word. The second rewriting system we call it morphological rewriter, or morph-R, and this is a morphological analyzer and generator that is built on top of a large manually created lexicon. For the last one, we use a neural rewriter, or neural R, and this is a word level sequence model that is trained with side constraints, meaning that for the input, we feed in a word and we prepend the target gender of the word that we would like to output. And since all of these rewriting systems are at the word level and are out of context, we would end up with multiple candidate sentences in the output. So we need to do a in-context ranking and selection step. And to do that, we use the approach defined by Salazar et al. 2020 to compute the pseudo-log likelihood scores over the CamelBERT MSA model to select the best output sentence. Now, in terms of our evaluation and results, we treat the gender rewriting task as a user-aware grammatical error correction, and we use the max match M2 scorer that computes precision recall on F0.5. And F0.5 here means that it weighs precision twice as much as recall, because we really care about precision in this task more than recall. And we also use blue. Now, for our baselines, we use a very basic do-nothing baseline that passes the input to the output as it is. And we also use a joint model that we developed 2 years ago that basically does sentence level gender identification and rewriting. And this model is a character level sequence model with word level morphological features. And in that model specifically, the target user gender is basically a relevant representation that is used during decoding. Now, in terms of the results on the def set, the 2 baselines, the do-nothing baseline, since it just outputs the input to the output as it is, it achieves a 0 F1, but a extremely high blue score of 89. This really indicates the high level of similarities between the input and the output. And this highlights the point that I mentioned earlier, where only 10% of the words were gendered. The joint model with morphological features achieves around 65 F0.5. Now we take that model and instead of learning a representation for the target user gender, we simplify it and we provide that information as a side constraint. We retrain 2 different systems, and we notice that The system in row D, the one that uses morphological features, achieve a better performance of 79 F0.5. Now for the multi-step model, we trained 3 different variants where all of them use the same gender identification and selection models, but they alternate in the rewriting setup they use. And we notice over here that the system in row E, the one that uses the corpus R model, achieves a performance of 84, which is the highest performance out of the 3 models. And that is mainly due to its high imprecision. Now, the corpus R and morph R model really suffer from the problem of added vocabulary because they're basically rule-based systems. So in order to mitigate this, we basically use all of the models in a cascaded back-off system. And the one in row I achieves the better performance of 88.11 F0.5. Now we take this best model and we retrain the gender identification and neural component on augmented data of around 800,000 sentences. And we do have more details on that experiment in the paper. And this achieves around 88.3 F0.5. Now, in terms of the results in the test set, we observed consistent conclusion where the augmented model was the best performing model of 88.4. Now, how can we use this in real life? We applied the gender rewriting system to post-edit the output of Google Translate to retarget it to different users. Now, the corpus, as I mentioned, does include English to Arabic Google Translate output. So we use our best augmented system to retarget the Google Translate output to different user target gender contexts. And if we look at the results in terms of blue, now if we look at the Google Translate result, we see that Google Translate is really biased towards masculine users, where it achieves around 13.6 blue scores. And there's a big gap between the feminine output of 1F2F. Now, when we write that, we achieve an average blue score increase of 1.2, where the highest increase is for 1F2F, and the gap between the masculine and the feminine output is reduced. So in conclusion, we defined the task of gender rewriting, and we presented a strong benchmark on it, and we showed a use case of how the system could be applied to real life scenarios. In future work, we would like to explore different models and apply this to different languages and other varieties. And if you think that this task is interesting to you, we are running a shared task at the 7 Arabic NLP workshop in MNLP, so please participate if you like this. And thank you so much, and I'm happy to take any questions you may have.
Okay, good. Time for a question. Please come up to the microphone if you'd like to ask a question.
Hi, thanks for the talk. I'm Anna from Amazon. So I was wondering if you could say more about how your test set is balanced and whether like the 1M2M and the 1F2F are the same data, just, you know, flipped in terms of gender?
Sure. So they are the same exact data. So we have human annotators who actually went through it to basically rewrite that data to create the opposite genders. So it's the same data, basically, yes.
Okay, cool. Thank you.
Sure.
So given that this is a human-computer interaction sort of a model, I would have liked to see the false positive rate, because I think that is like, you know, there are lots of numbers with F-score, precision, recall, but when you actually interact with the device, right, what you're really looking for is you want your false positives to be very low because you know what the user's gender is, and you don't want to misrepresent that. So I'm just wondering if that's something that can be done as part of the workshop, or perhaps like, you know, in terms of how the results actually look, what is the false positive rate that you know can be reported in that table, because it's like an easy thing to absorb when you design systems.
So you mean like to present results on the error analysis to see how the model is doing on different...
Just the false positive rate, because what the user is going to experience is it wrong, right? I mean, rather than the precision recall, it seemed to like standard numbers that I see in all the papers and tables. I think looking at false positive rate is a good way of looking at what is the user going to experience. It's just a point I wanted to make in terms of how some of these systems can be evaluated.
Sure, we'll look into it. Thank you so much.
All right, let's thank our speaker.
Sure.